Okay, so let's look at network forensics and protocols and really try and understand how networks work and how the protocols can be used to understand the communication trails. So we'll look at the core protocols, and these include IP and TCP, along with ARP, and then we'll go to the high-level protocols such as FTP, ICMP, DNS, and then right up to the application layer, which is the protocols such as HTTP. But before we start, let's take a very simple look at how two computers communicate. So let's say that Bob wants to communicate with Alice. So we need to get the data from here to here in a reliable and consistent way. So each machine on the internet has an IP address, and the IP address is used to be able to locate the destination, either a local address or a remote address. Then what we have is a physical address called a MAC address, and we need to be able to resolve both of the addresses to be able to finally deliver the data to a destination. So most computers will connect to a switch, and the switch itself connects multiple computers onto the same network. When one computer wants to talk to another computer, it will send out an ARP request. And the ARP request goes normally across the switch, and all the computers which connect to the switch will hear that ARP request. In the ARP request, there is an IP address defined. So the computer who wants to communicate with the other computer sends out an IP address to the network, and the machine with that IP address responds back with its MAC address. Once it does, then we have what's called the ARP cache, and that then stores the resolution of the IP addresses to the MAC address, and once that's resolved, then the machines can communicate. Every so often, every few minutes, the ARP cache is refreshed, unless it's a static mapping, and it will be rediscovered. In this way, the internet is dynamic, and that we can change network cards and so on, and devices will be aged out of the network. Then what we have is that we connect to a router, and it's this device which will allow us to be able to interconnect networks. So these routers will interconnect in some way, and they will intercommunicate and tell each other the best way to get to a destination. So if we draw a switch over here, and then we connect that into the switch, and then Alice will connect to there. Okay, this port here is known as a gateway port. This is the way for Bob to get out of the local network and then on to the internet. So Bob will send out, he will know hopefully the IP address of the gateway, the port and to the router that he connects to, and then the gateway will reply back with its MAC address. Once it has the IP address and the MAC address of the gateway port, then it will now communicate with that port to be able to send data over the internet. So in some way, Bob discovers Alice's IP address. Typically that's done, say, through DNS, where Bob will ask for a domain name, and he will get back an IP address mapped to that domain name. So when Bob now communicates with Alice, then we will take the data, and the data is then segmented up into a number of segments. Each of the segments is marked with a number. We'll just mark them 1, 2, 3 just now. So these are known as TCP segments, and each segment is marked in a certain sequence. So the different segments could take different routes across the internet, but could be reassembled back at the other side because they're ordered. Each of the segments then has an IP address applied to it, and then can be sent within an Ethernet frame. So the Ethernet frame travels across each of the networks. We have the destination IP address of Alice, but the local MAC address of the gateway in this case. Then the gateway will look at the IP address and decide that the best port to send the data out might be this one here. It will then create another Ethernet frame, if it's an Ethernet connection, with the source address here and the destination MAC address here. It will take the IP packet and send that over the internet or to the next router. It will then forward it to this port here, and our data frame will move on. The source and the destination MAC addresses are defined. Each of the routers will discover the other side through the ARP request and will hold their own ARP table. When it comes to this port here, this router must now determine the MAC address of Alice's machine. So it will send out a MAC address and ARP request onto the network, and then Alice's machine will reply back so that it can resolve the MAC address of Alice's machine and then be delivered. Once it's delivered, we will then be able to unpick the segments back and reorder them. And it's at this level here that Alice's machine will send back acknowledgements to Bob's machine to say that she's received those segments and there are none missing. If one goes missing, Alice can reply back to say that it will only acknowledge up to the one that's missing, so that Bob will resend the data segments. Okay, so that's a quick overview of how networks actually work. Let's look at the core protocols involved. Now, overall, we have a layered approach to building our networks. This makes it easier for us to interchange hardware and software. So at the lowest layer we have the physical layer, which is obviously copper or increasingly fiber optic cables. Then above that we have the Ethernet layer. As we saw, this is the protocol that allows us to be able to transmit what are called data frames between two computers. It's basically a reliable way to get data across a local network. At the layer above, we have the concept of a network address, and we have packets at this layer. So we see IP packets across the network, and these will be routed through the network. At the layer above this, we have TCP segments. These are the chunks of data that are transmitted and are numbered. At this layer, we have reliability built into the system, so that if we lose any data or if it gets corrupted, then it will be at this layer that we'll be able to detect that and overcome any problems. And then at the layer above, we build our protocols such as the web for HTTP, FTP, Telnet, and SMTP for email. The way it works is that we start off with our data. We chop the data into the segments sizes that are going to be required, and then we'll transmit it through adding each element of the layer as we go. And then at the data link layer we add a header and a footer, and it becomes a frame, and then it will be sent across the network. This is known as data encapsulation. So here are the basic fields that we have with Ethernet, IP and TCP. So we typically show an Ethernet frame along this way, but we show TCP and IP headers stacked up like this. This is 16 bits across here that I've identified. So we initially start with a preamble with Ethernet, and then we have in here a 6-byte MAC address and a 6-byte source address. These MAC addresses, 3 bytes identify the manufacturer, and 3 bytes should be a unique ID for the device. This can also be a software defined MAC address, where it's not actually burnt into the hardware but is provided through software. And then to support higher level protocols, we have a type field, and in here if it's 0x800 it's IP that's going to follow. If it's if it's 806 in hex, then we have an ARP packet, and obviously what comes after that differs, and we'll have a look at that in a little minute. For the IP header, the first 4 bits define the version number, and we either have version 4 or version 6. Version 6 is a completely different header and has a longer IP address. Then we'll see other parts of the header, such as the 32-bit IP source and destination address. In here we also have the protocol field, and the protocol field will define what's coming next at the higher level. So it can be TCP, but it can also be routing protocols such as EGRP. It could also be UDP or ICMP. So if I have a value of 6 here, then what we see next is an IP field. Then we have a 16-bit TCP source. So that's from 0 to 65,000 and odd for the port number. The way that the internet works is that we have an IP address on either side, and we have a TCP port. The binding of the IP address and the TCP port should be unique across the whole of the internet. Then we have these sequence numbers here, which will define the segment numbers that we have, and the acknowledgement numbers are the things that go back to the other side to acknowledge that data has been received. And then we have the important area of the flags, and we'll be looking at these a little bit later. So it's these 3 protocols that really make up much of the internet. At the core of a client-server architecture is the connection of a client port to a server port, and it's this port that is used to be able to communicate the data segments. This is initialized with the SYN flag in the TCP header. If you remember, we had some flags here. Within there is a binary SYN flag. Then the client, if it wants to accept the connection, it sends back a SYN-ACK, and then the client acknowledges this with an ACK. This is what's called the 3-way handshake, and after this we should have negotiated the port numbers that we're going to be using for the communication. So when data comes in for a certain port number, then the server knows that it's related to a certain connection. Along with that, we can also set a window size, and the window size is the maximum number of segments that we can send before the other side has to wait for an acknowledgement. So let's take an example here. So we start off with a sequence number, an acknowledgement number of 0. Then the server sends back its own sequence number of 0 and sends back an acknowledgement of 1. The 1 identifies that it's expecting to see sequence number 1 next. So that it has acknowledged everything before that, which is obviously the first sin in this case. And then the data will go back and forward. In this case, we acknowledge 28, so that the next sequence number we expect from the server in this case is the sequence number 28. And we can see here this is acknowledging up to 21, so it's expecting to see 21 next. So in this way, we go back and forward acknowledging data as it's sent. If something is missing or has not been acknowledged, then the other side will resend all the unacknowledged data again. If that still doesn't get acknowledged, then the connection will be cancelled. Okay, so the first protocol that we look at is an extremely important one called ARP. And with ARP, we connect to a local network. And in this case, we have a switch and a router here. And here is the gateway port on the network. So if a computer wants to know the MAC address of another computer, but it knows its IP address, it sends out an ARP request to the whole network. So in this case, Bob wants to know who has that address. So that's sent out. It is broadcast across the switch to every port, and across here. It will eventually go to here and stop. In this case, we see that we start from here with the request. So the request is coming from this port here and asking for the MAC address of this computer. So when the broadcast goes out, then it will go across the whole network, and Bob's computer here will reply because his MAC address is here. And then that will be a reply back to that address there. Okay, so here's an example here. So we see a request going out. So in the request here is asking for the MAC address of this machine and to tell this machine. This is the broadcast that we see, which is all Fs onto the whole network. The ARP table itself, we can see that there are some dynamic things and some static things, but once we get the MAC address of that machine, it will map itself into the ARP table with the MAC address. So the reply that comes back is from the machine at that address, and this will be the reply that comes back. So we'll have a look at an example of this. Okay, so here we have an ARP. Okay, so we have Ethernet here, and as I said, within inside the Ethernet packet, we will have a type of 0806 for ARP. So the next thing that appears is ARP. Okay, so in this case, the address which is being asked for is 192.168.47.4, and we have to tell this machine here. Okay, so here's one here that we're asking for this address, and we want to tell this address, and then the reply that comes back is from that machine. We can see the MAC address here. Okay, so in this way we can actually see the first signs of a network connection across the network. In this case, this is identifying what looks like an ARP scan. So a host is scanning the whole of the network and asking for addresses. And we can see here, this is an example of a reply back from this machine here. So we can actually look at certain parameters within the search. These are defined here. So we might want to look at the opcode. And we can see an opcode of reply of 2 is here. So we'll go for an opcode of 2. And that gives us the replies. Okay, so if we wanted to go for an opcode of 1, or if we look at the other opcodes, we see an opcode of 1 here. These will give us the requests. Okay. So one of the most basic elements of a connection is the SYN, and the SYN flag is sent at the very start of a connection. So this is what happens here. When we make a connection, the client sends a SYN flag to the server replies with a SYN ACK, and then we get an ACK back. So let's have a look at a sample of this. Okay, so we can see a few SYNs in here. Okay, so we'll pick this one here. So in this case, we see this SYN, and then a SYN ACK comes back. If we look at the ports, and then finally there's an ACK coming back from the server. Okay, so it's a SYN ACK, and then an ACK. This is the client, and this is the server address. Here, there's the server and the client, and then eventually the client replies back. So one thing that we can do in Wireshark is that we can follow a stream, and this will take us through the whole connection from the SYN being sent to the end of the connection. So the red is generated from the client sending, and the blue is what the server sends back. Okay, so if we just look at the basic SYN itself, so there's our Ethernet. So the Ethernet will be the destination MAC address will be for the gateway in this case. And here is the IP4. So we see we're using TCP of 6. Again, we can say TCP dot protocol, sorry, IP dot protocol. Equal to 6 would give us all the TCP packets. But then if we look at the TCP part, we actually see here is the source port and the destination port. There's the sequence number there. This is the flags that we see, and we should see that we're using a SYN flag in this case. The next one that comes back will be a SYN ACK. So we see here a SYN and an ACK from the server, and then finally we get an ACK from the client to the server, and we see things like the sequence numbers being exchanged there. So we can see there are sequence numbers, that are defining the data segment flow. Okay, so here's an example here of a SYN connection here. We see a SYN ACK and then an ACK there. Okay, so this is the client, this is the server. Server responds back to the client, and then the client responds to the server with the ACK. So we then have a connection between this port on the client and this port on the server. If we now move up, we move into FTP, which is moving towards an application protocol. And within the application protocol, what we actually see is a whole lot of commands and responses. And we'll see this is so important when we look at our cybersecurity alerts, because it's often the responses that come back from the server that allow us to be able to find things easily. So within FTP, really the client sends certain commands such as get or put. Get gets a file and puts a file onto the server. Remove directory and so on. So these commands are sent from the client to the server, and the server responds back with a certain code, a status code. 200 codes are normally there's been a success. 400 codes means that the action hasn't happened and there's been an error, and 500 codes means that there's probably been a problem with the server itself. Some of the well-known codes are 200, means everything's okay, so the command was accepted. And then we see other ones, such as 230 when a user logs in, or 2331 when the user is logged in but needs a password, and so on. So it's these codes here that we often look for in terms of our logs to be able to see what's the status actually is. Okay, so here's an example. We connect to the server, we get a 200, then we type in the command user administrator, we get a 331, then we are asked for we enter the password, and we get a 230. 230 means that the user has logged in from there. Then we do some commands such as show the current working directory. Now what happens with passive FTP is that a new port is opened up for the connection for the file to be transferred or for other information to be passed. In this case, we look at these two numbers here, and the port that's opened up on the server is 4 times 256 plus 22 in this case, which is 1024 plus 22, which is 1046. So the client connects into port 1046, makes a connection with it, and will download the information that's actually passed, and then we'll close the connection. So port 21 is what we use for FTP, and it's only used for passing these commands. The actual data that needs to be transferred is passed through ports that are set up on the server. Okay, so here's another connection being opened here, and another one here. Okay, so there's the example here. 4 and 23, we're opening up port 1047, we make a connection, and then we'll download the file or the information that's passed from there, and we'll get a 226 on that. So let's look at an example of this. Okay, so this is an FTP trace, so you can see there's the port 21 connection, there's the SYN, and there's the SYN ACK. Then what we'll see is the commands that we saw before for passing things back and forward. So what we'll do is we'll trace from here and follow that stream. Okay, so here's the commands that we see. And we'll see here that there doesn't seem to be any files actually transmitted or any information transmitted. In this case, we're asking for a list of the files on the system, but it's this connection here which is opened up that will actually pass that information. So if we trace down, we'll see a connection happening that will show us the file being transmitted. Okay, so there's entering passive mode, and look here, we get a connection on port 1081, which should relate to this one here. If we now look at this connection, we'll see what we get. And we can see here, this was a listing of files from the FTP server. Okay, so FTP opens up, passive FTP opens up a server port, and we connect into it and we will download the information. Port 21 is really only used to be able to pass these commands. Another important protocol is called ICMP, and this allows us to be able to debug getting things like traceroute or ping. With this, we have a request and the reply. So we have certain types, and a type 8 is an echo request with a certain sequence number, and then in this case we're asking a device to reply. It replies back with matching the sequence number here back. In Windows we have a payload of the alphabet repeated. So we'll have a quick look at what ICMP looks like. Okay, so here is a request, and there is ICMP. So we can see that ICMP sits above IP version 4. IP is a layer 3. So we would often define ICMP as a layer 3.5 because it isn't quite a layer 4 as TCP is. Okay, so we're getting an 8 here. So if we wanted, we could look at ICMP dot type equals 8. And we see all the requests here. And now we need to look for a reply coming back. So we can see lots of requests. We need to find our reply. So reply is 0. We don't actually have any replies here. These are just requests going to the whole network here. So what we'll do is we'll just grab any ping here. Okay, so here's a ping request, and there's the ping reply coming back again. Okay, so there's the 0. So it's ICMP dot type equals 0 will show us all of the replies coming back, and then if we use the other one, that gives us the requests. another important protocol is DNS, and DNS is the protocol that allows us to be able to resolve a domain name or a domain host name into an IP address. And this uses UDP and port 53. So we need to make sure that that's unblocked on the firewall for us to be able to communicate. And with this, whoever owns the domain will create a record, an A record, and will actually define the IP address that relates to that domain name or to that host name. Okay, so we get a request, a query that gets sent out, and then the DNS server will reply back with the IP addresses that could be used for the domain name. Okay, so we'll have a quick look at what that looks like. Okay, so here's a request here, a query getting sent out here. This is the query here for intel.com for the A record, and the response back is here, and we can see here it's returning back the IP addresses that would be provided for that domain name. Once we have that, we could probably communicate with the server. What we see is port 53 is used on the server, and we use our own UDP port here for the communication. We can see that each one will have a unique port on the server, but we always send to the DNS server with port 53 in this case. Okay, so there's a number of things that we should look for in our network traffic that could show maliciousness, and that's with a port scan. And one of the tools that's used for a port scan is Nmap. So Nmap will go out and scan the whole of a network to find the hosts that are alive, to be able to find the ports that are enabled, and so on. So we'll have a quick look at what an Nmap scan looks like. Okay, and here it's here. So in this case, what's happening is the Nmap is sending out a whole lot of SYNs to this one host here. So Nmap is on here, and then is scanning all of the ports on this host here. So we see all these SYNs. If we see a reset ACK from the server, it means that it isn't actually open. If we see a SYN ACK, then we have a port that could be connected to. So here is one here. We'll see a SYN ACK coming back from port 80, from 135, and from 53. So these ports are open, where these ports are not open. So if we wanted, we could look at TCP dot flags dot SYN is equal to a 1. That shows all the SYNs. And then if we want to now look at the ACK coming back, then we'll also look at SYN ACK. Okay, so this is a quick way for us to be able to find the ports that are open. So you can see in this case, port 23, 445, 1025, and so on are open in this case. Okay, so we can very quickly search Wireshark traces for these types of activity. So there are various types of port scans that can happen. There's a TCP scan where Nmap will reply back with an ACK and then close the connection with a FINAC. But we can also get an open, a half-open connection where only the SYN is sent, and even though the server responds back with the SYN-ACK, the Nmap doesn't reply back with the ACK. And we can also get a FIN scan where a FIN flag is sent each time. Okay, so a port scanner goes out to the whole to a host or a number of hosts and tries to see if certain ports are open. We can also get a port scan across a port sweep across the network, and this is where an intruder is only interested in one port and then might sweep across all of the machines on the network looking for a connection. Finally, there's a SYN flood, and a SYN flood can be seen as a denial of service. In this case, we'll get lots of connections to a host, which will reduce its performance, and it may be that certain connections will be blocked because the server is trying to cope with all the connections that are involved with the denial of service. So I'll have a quick look to see what this looks like as a trace. And we see here lots of connections just with a SYN on there. In this case, we're connecting to port 0 with the SYN, but in most cases it will be targeted towards a certain port, such as a web port. And then we move up into the application layer, and at this layer we start to see the higher level protocols. So one of the most significant is HTTP 1.1 is the most common. For this we send a command such as a get slash, which is actually asking for a certain top level file, and then we add certain parameters onto that request, which aren't really seen from the browser, but add things on such as the host IP address and the files that the browser will accept. When it comes back, we see the status code coming back, and then we see additional information which will actually define the contents, any attachments, and so on. So if we have a little look at what that looks like, the main commands that we get are for HTTP are get and post. So get is where we get a web page from a URL, and a post is normally where we click on a button or a form and it will post back parameters into the page. Okay, so here's an example here of a connection. So we'll just look at one connection here. Okay, so this is the get that we have from the client. This is the additional information. So the connection keep alive means that the TCP connection isn't broken, but it's staying alive because we want to communicate with the server later. And this is what actually gets response back with. A 200 means it's okay, and then we get some extra information. And we'll see later on when we look at our Splunk analytics that we can use all of this information to be able to understand the state of the connections. Okay, so that's been a brief introduction to network forensics and protocols.